Okay, let me start by thanking the organizers Satyabrata and Poonam for inviting me to this very nice conference. Today I'll talk about Fermi arc connectivity and transport in wild semimetals. Let me first start by just giving the main message. As many of you know, wild semimetals are famous for Fermi arcs, which are these surface states, very unusual surface states. But the connectivity, and that is determined by topology, but the connectivity of the Fermi arcs is not completely fixed by topology. And when you put different wild semimetals on top of each other, how the Fermi arcs get connected contains much more information, and that's what I'm going to be talk about over here. And also whether that connectivity at the Fermi arcs, which is actually in the middle between the two samples, whether it can be measured. And we'll see that transport can actually give some indication of how the Fermi arcs get connected. So I'll start with the motivation and introduction, and then I'll discuss what happens when you have junctions of wild semimetals, one on top of each other, and how the Fermi arc connectivity works. Then we'll discuss transport through junctions. So yeah. I'm giving a general introduction since not everybody may be working on wild semimetals here. So as you know, what are wild semimetals? And you know that the relativistic Dirac equation in 3+1 dimensions describes spin half particles, and this is just the relativistic Dirac equation. In the massless limit, this splits into two components. I've forgotten a gamma mu here. It splits into two component equations, Hamiltonians, one with a c sigma dot p and one with minus c sigma dot p. And the essential point, the only thing I want to mention over here is that the Dirac cones with a fourfold degeneracy can be gapped out by perturbations, in the sense that I can add a mass term, but if you separate the two parts of the Dirac cone into two wild nodes, then either in momentum space or in energy space by breaking either time reversal or inversion symmetry, then each node is described by a wild Hamiltonian. And so essentially now you have, in terms of these two components, there's no fourth anti-commuting matrix possible to add a mass. So what happens is, if you add perturbations to this, it can only move the wild nodes around, but actually cannot gap it out. You can get a mass gap only when the two wild nodes come together to form a Dirac node. So you have gapless fermions with opposite helicity at each node, which is actually genuinely like wild fermions, the kind of wild fermions you also use in high energy. This is unlike Majoranas, where the Majorana modes we talk about in condensed matter are different from what is discussed in high energy. The stability of these wild nodes is connected to a topological quantum number, which is its chirality, as long as you cannot have intermode scattering. And they are kind of monopoles in momentum space with quantized Berry flux of 2 pi kappa, where kappa is plus minus 1, is the chirality. And the topological stability is simply because of Gauss' law. Whatever comes in has to go out. So around each wild node you have topological stability. One can get band structures. I just wanted to, since the focus will be on Fermi arcs, I wanted to show you what these states are. For a topological insulator, this is the kind of band structure you get. For a Dirac semimetal, this actually it's a metallic, so you don't have any gap to excitations. But for a wild semimetal, you have a gap to excitations between the two wild nodes, but they are states, they are surface states, which have some kind of they're flat along one direction, but they have dispersion along the other direction. And these are the Fermi arc states. And these are very unusual because they actually, as you can see here, they terminate at the wild nodes. And if you take the surface Brillouin zone, they will terminate at the wherever the projection of the wild nodes on the surface Brillouin zone. And so at the wild nodes, you can see that essentially the Fermi arcs merge into the bulk states. And the states only exist for a restricted range of the momentum, and they form an arc and not a full Fermi surface. So the intuitive picture that you can think of is to start with a full Fermi surface on a thin slab and then pull it apart and think of the Fermi arc states as part of it stuck to the top surface and part to the bottom surface. More correctly, what one can see is that between the two while nodes, if you think of any 2D plane between the while nodes, it will have a very flux passing through it. So the Chern number along those 2D planes it will have a Chern number of 1. So if you string together all those edge states, it will form a Fermi arc. So this is the Fermi arc on the surface Brillouin zone. So, and these are not, I just wanted to also mention that there is actually experimental evidence for these Fermi arcs, and they've been seen by Hassan et al. In tantalum arsenide as early as 2015, and now they've been also seen in tantalum phosphide. The only point that you have to realize here that they cannot be removed without removing the bulk while nodes. So in that sense, they serve as surface fingerprints of the topology of the bulk system. Now, this is all actually very old knowledge, has been known since about 10 years ago. But what is much less known is what happens when two while semimetals are put together. And what we wanted to study is whether there are new interface states which are formed. Are they topological? Do they carry current? Right? So that's the question that we are asking. So what we want to study here is junctions of while semimetals and Fermi arc connectivity. So what happens if you have a junction of two while semimetals? You can bring them together, since they are and then you can turn them, twist them. This is like the graphene experience. We know that you can bring together two graphene sheets and turn them. So similarly, we can bring together two slabs of while semimetals and turn them, and then you can actually have a tunnel barrier between them. So for a single while semimetal, as I already said, the Fermi arcs connect the two projections of the while nodes with flux lines either entering or leaving the surface. From here you can see that you have a Berry flux coming out. It goes to the surface Brillouin zone, and then the Fermi arc connects it to the other while point projection, and from there it can go in. Now, what happens, the question that we want to now ask is what happens when you put two while semimetals on top of each other. And from the experience over here, you can see that these Fermi arcs are chiral, they move in one direction. So in the same way, if I think of having two while semimetals, one on top of the other, then the question that one can ask is whether the plus of this, whether the plus of this should be connected to minus of this, or plus to plus, and so on. And if you look at the the projections, what you see is that essentially from here the projection goes downwards. From here, the same plus chiral gives you the projections which go upwards. So it is necessary that you have this homochiral on the interface. The Fermi arcs get connected in a homochiral way, because if you have something because you have a flux coming up at one while point projection and going down the other projection. The heterochiral case will have flux going down in both cases or going up in both cases, in which case it cannot get connected. So this argument can be made much more rigorous by using Chern numbers of imaginary cylinders around the while point, but I don't want to do that here. It is pictorially easy to check that you will get homochiral projections. So essentially what we studied was the evolution of Fermi arcs as a function of the tunnel coupling between the while semimetals, and for different angles. The simplest angle you can think of is what happens if the two while semimetals are 180 degrees rotated with respect to each other, And then what you see is that as a function of the tunnel coupling, we can get, you see the evolution of the Fermi arcs as a function of the tunnel coupling. And again, if you, some of these unfortunately have been put wrong. These are plus and plus, this is minus and minus. And at theta is equal to 90 degrees, when there is no tunnel coupling, the plus and minus of one get connected to one another, the plus and minus of the other get connected to one another. But once you introduce tunneling, it's the homochiral coupling which happens, and the Fermi arcs get connected in this way, and then you can see what happens as you change the coupling constant. We can actually, in the initial work with Farooq and Ganpati, we looked at very many possible commensurate angles where we could get supercells. And in terms of the supercells, you can explicitly compute these things. And what we find is that you can check out what happens at how the Fermi arcs evolve as a function of the coupling. It can evolve in all possible ways, and we can even have isolated Fermi loops besides the Fermi arcs which are connected to the Weil point projections. And we can also have cases where all the interface states are completely decoupled from the Weil points and form closed loops. This was first conjectured for special incommensurate twist angles by Murthy, Fertig and Shimshoni, and we later found that there are many cases like that. So just to summarize, we get different kinds of Weil point on the interface, while connectivity on the interface. We can have open Fermi arcs, we can have open Fermi arcs along with closed Fermi arcs. This is an example of an open Fermi arcs, and this is actually a closed Fermi arc because these two edges are identified. It's a Brillouin zone. We can also have Fermi arcs which are completely detached from the Fermi point. So all these kinds of things are possible. So many possible connectivities at the interface. But how are these but the problem is that these happen at the interface between two Weil semimetals. The question is, how can these be seen in any experiment, right? So we recently asked the question of how do these different connectivities show up in transport? Do they carry current? And transport, we looked at the case where there is no connectivity between the Weil nodes. So here both all the Weil nodes states are connected. So we looked at a region where each Weil node is isolated, so at very low momenta in fact. And because in the Weil semimetal you have both surface states as well as Fermi arc states, as well as bulk states, right? And we want to kind of confine our attention only to the surface states and not have bulk state transport. So we will restrict our attention to conductances where the Fermi pockets of the Weil semimetals do not overlap, because our focus is to understand Fermi arc connectivity. So in this regime, if there are no interface states, there is no transport at all. So our question is to study how current gets transported through the interface. So first, in the absence of magnetic field, we've taken the role, we've chosen the pi/2 rotation angle so that you can actually isolate the role of interface transport, because when two slabs are now decoupled, any upward moving state, the only thing that can happen to it is that it will come down, and if you now tunnel between these two, the only way the electrons from a lower slab can get to the upper slab is via the transverse Fermi arcs are on two different directions, right? Because I've taken a 90-degree rotation. So essentially it cannot go through to the other case. If I had not taken a 90-degree rotation, then via the transverse slab there could have been some kind of transport. So here, because I've taken a 90-degree rotation, the transverse surface states are perpendicular to each other, and you cannot have any transport at all, and all states on this side have to get completely reflected. Only with tunneling now, the surface states have to hybridize to get from y is equal to 0 and go from here, they go there, and then they need some hybridization to go to the other one. And that is what happens over here. We see that there is hybridization between the surface states of the lower slab and the upper slab, and essentially when you compute conductance, we find that there is non-zero conductance depending on how much of this hybridization takes place, and this is kappa here is the tunneling. The peaks are when the reconstructed Fermi arcs are straight lines. In these cases, what happens is that the straight line Fermi arcs imply that the electrons slide parallel to each other and don't scatter, so conductance gets maximized. And we also find that there is a high kappa, low kappa duality in the picture, because when there is very high tunneling between the slabs, then the two surface layers get hybridized, and they get to be a high energy state, and then the next levels have to go through that very high tunneling barrier. So it's like as if you'll have a 1 by kappa, you'll have a t squared over kappa. So that gives you this, because high tunneling forms a barrier for the tunneling of the next two states. Now we can also look at what happens when you have in the presence of a magnetic field, and maybe this is not something I need to say. Basically what I wanted to say is that there is a chiral anomaly in the presence of a magnetic field, and in the condensed matter language, the way this manifests itself is as a spectral flow of the chiral 0th Landau level, which disperses either parallel or anti-parallel to the magnetic field depending on the chirality. All higher Landau levels have both states going up and down, both left and right chiralities. So what happens for the while semi-metal junction, electrons move along the positive direction in the lower slab, they reach the interface, slide along to the while node of the upper slab, and then continue to move along the positive direction. So in while semi-metal junctions, the chiral magnetic effect and the Fermi arcs combine to transport chiral electrons from the bottom to top. This is the way the transport goes because of positive chirality or boost. So via this transport, we can actually get a signature of the chiral anomaly. And this gives rise to a universal conductance which only depends on the number of chiral Landau levels. All higher Landau levels have both states which are go up and down, both chiralities. It's only the 0th level, it has no counter-propagating propagator, so it must continue, so it goes into the upper level. So only the 0th chiral Landau level leads to transport. And this conductance is universal as long as there is no backscattering, and the derivation only breaks down when the magnetic field is large enough to enable backscattering, which means that you will have backscattering between the Fermi arcs. So for close encounters between Fermi arcs, the universality breaks down when the magnetic length is in the same order of magnitude as the distance between the two Fermi arcs, right? You can have a distance between these, and if these two are comparable, then the conductance comes down. And but this earlier derivation neglected transverse surface states, and for a finite sample, there are also non-interface surface states that can carry current, as we saw without the magnetic field. So those surface state contribution also has to be included. And what we found is that without the surface state, if the conductance as a function of the magnetic field goes up like this, with the surface states at very low magnetic fields there is a correction. And the correction is actually, this could be done by doing it, keeping the system periodic, whereas here we made one of the directions non-periodic, but since the two are in perpendicular directions, we needed to make only one of them non-periodic. So surface states are important when the number of bulk states is roughly equal to the number of surface modes, but that of course is not always true, because this is the number of bulk modes is proportional to Lx times Ly, the full surface area, whereas this is only linearly dependent on the length. So this kind of thing would be true, would be relevant only for mesoscopic systems where the lengths are very small. So in the last part of the talk, I'll give the latest work where we've tried to see is there some place where surface states can dominate over bulk transport, and that can happen if you have a wild semi-metal layered churn insulator junction. Because if you have one of them to be a layered churn insulator, a layered churn insulator is a stack of 2D insulators where the bulk is gapped and it only has transfer states. So in that case, the Landau levels in the bulk of the wild semi-metal cannot go through the bulk of the linear churn insulator, layered churn insulator, because it does not have any bulk states. So the only way it can get transported is via the surface states. So at the junction, what happens is that the chiral zeroth Landau level are redirected by the interface states to the transverse surface states. And this actually happened, we showed that this can also happen for a wild semi-metal junction when one of the wild semi-metals is driven into a layered churn insulator state. We've actually ignored disorder. I mean, a lot of the computations here have been done using quant, and we've ignored disorder, but because the conductance in these cases are all topological, in the sense they're determined only by the number of modes. So we have not worried about which is a topological invariant. So to conclude, I mean, what we've looked at here is we've studied the reconstruction of Fermi arcs at the interface. And one of the things I wanted to emphasize is interface Fermi arcs connect same chiralities, which is different from what happens in a normal wild semi-metal, where they connect opposite chiralities. They provide only transmission for the chiral Landau levels, and their connectivity connects magnetode transport. And finally, layered churn insulators give rise to universal conduction at saturation. Thank you. I finished in time.
Thanks, Smriti, for finishing in time.
So, two questions maybe. Number one is, can we, means when we stack one semi-metal, wild semi-metal with the other, can we treat the entire two as one semi-metal? Can it be possible that we have just the Fermi arcs on the ends of the two semi-metals, and at the interface we don't have any?
That will mean that it's a single. I mean, if there is, if there's no twist, and if there's the hopping between the two semi-metals is the same as the hopping within the semi-metals, then it's one. But the minute you change it, then you will have an interface, right? If you change either the angle or the hoppings, right, that will give rise to an interface.
And the second question is, if we stack the, like here we took the wild semi-metals, I don't know, the charges were the same, like we can have higher churn number wild semi-metals, like one with +1, -1, other with +2, -2.
Yeah.
And if we stack them,
then also you will get interface states, and then the connectivity will depend on, there is a way to compute this Fermi arc connectivity. I mean, I took the simplest case where I thought I could show it pictorially, but yes, what you can calculate is what is the churn number of the thing which surrounds the a cylinder which makes between the top and bottom, and the same argument for a single wild semi-metal, there is an argument involving churn numbers. Here the same argument, what you have to do is make it as a difference in churn number between the top layer and the bottom layer. It gets replaced by that. But yes, it depends on what are the churn number of something which is surrounding these while nodes.
Thank you.
Yeah. Thanks, Mosik. Nice talk. So, just one question. If you are exactly half filled, at the pristine point, then your surface states are going to dominate anyway, right? Because
yeah, exactly. Yeah, it depends. I've taken some range around the this thing. Yes, if you're exactly at half filling, surface states will dominate.
Because it's just 2 points in the bulk, and the density of state goes to zero.
Zero. Yes. Yes.
Whereas surface state is a line, so I was thinking that maybe that would help actually.
No, but okay, that is true. I mean, what I was trying to say is that even then the surface states, it depends on the surface area, right? Yeah, we never worried about the bulk, which is the 3D bulk. But the comparison I was doing between this one, this is the surface area, because there's a magnetic field and a surface area. Whereas if you think of the things along one line, one of those transverse things, it depends only on one of those two linear dimensions. So there's still a difference in linear dimensions between this one and this one. It's not Lx, Ly, Lz. That's what I meant.
Thank you.
Are there any more questions? Okay, if not, then let's thank Sumati for this very clear talk. We move on to the next talk of the session.